AM or amplitude modulation and FM or frequency modulation are ways of broadcasting radio signals. Both transmit the information in the form of electromagnetic waves. AM works by modulating the amplitude of the signal or carrier transmitted according to the information being sent, while the frequency remains constant. This differs from FM technology in which information is encoded by varying the frequency of the wave and the amplitude is kept constant. In this video I will going to brief you difference between amplitude modulation and frequency modulation. AM involves the alternation of the amplitude of the carrier wave, whereas FM involves changes in the frequency of the carrier wave. AM frequency range from 535 to 705 kHz or up to 1200 beats per second, whereas FM frequency range is higher spectrum from 88 to 108 MHz or 1200 to 2400 beats per second. AM waves have a much larger range and can therefore be received even in hinterlands. This is the reason most news stations use AM over FM. Whereas FM waves have a small range in terms of the geographical region they can cover. AM signals take up 30 kHz while FM signals take up 80 kHz of bandwidth for each signal. AM waves transmitter and receiver can simply by synchronization is needed in case of SSBSC AM carrier, whereas transmitter and receiver are more complex as variation of modulating signal has to be converted and detected corresponding variation in frequencies. AM is more susceptible to noise because noise affects amplitude, which is where information is stored in the AM signal, whereas FM is less susceptible to noise because of information in an FM signal is transmitted through varying the frequency and not the amplitude. Dear viewers, thanks for watching the video. Any question, write in the comment box. Don't forget to like and share. More update, please subscribe our channel Learning Engineering and get notifications to.
Okay, if you see, this actually more compared to my time. Now it's easier if you want to learn from other sources. Okay, you don't have to listen to me only, and you don't have to learn only from me. There is a lot of sources. Okay, where you can help you to to increase your understanding and also for you to do more practice. Okay, online exercise. Okay, now we go to this angle modulations. Okay, angle modulation is the frequency modulation. Okay, so we have frequency modulation and phase modulation. Okay, so later we go to it. Okay, in AM modulation, we varying the amplitude of our carrier is following our modulating signal, and our information is lies within the amplitudes. Okay, the envelope. Okay, the amplitude. So it is more susceptible to noise because when we go through when we transmit and there is noise. Okay, so the amplitude often impacted. Okay, so that's why it is susceptible to noise. However, in the frequency modulation, the one that we vary is the frequency of our carrier, which following the modulating signal. Okay, so it is less disturbed by noise, because we are not storing our informations at this amplitude, but we store it as a varying frequency. Okay, uh, and then you can see from the YouTube just now, okay, why the even though AM is more susceptible to noise, but why it is being preferable to be used for the news, okay, for the news station, okay, because it can cover large area, right? The video told just now. But there is some advantage and disadvantage of AM and FM. FM, even though it's less susceptible to noise, but it is more complicated, more complex. And you can search for more for advantage on and disadvantage of AM and FM. We never know if the question asks you what is the advantage and disadvantage, right, for AM, FM. Why? What is pro and cons of both of these modulation? Okay, okay. So we're going to start with new chapter, which is the angle modulation. Okay. So angle modulation. So before this is only amplitude modulation. So beside AM technique, other well-known modulation technique is known as angle modulation. So angle modulation, or we can have other name, is exponential modulation. Uses modulating signal to change frequency. Like I told you just now, the frequency is being varied, and also phase. Okay, frequency and phase together they are angle modulation. Okay, angle modulation or exponential modulation use modulating signal to change frequency and phase of the carrier signal. In contrast with amplitude modulation, okay, the carrier is being changed in terms of its amplitude following the modulating signal. In FM, in frequency modulation, the carrier frequency and phase is varying according to the message signal, according to the modulating signal. Am I recording this? Okay. So introduced in 1931 by Edwin H. Armstrong. Okay, you can, if you're interested, you can search yourself for the history. I'm not going to talk so much on the history side. Okay, so generous sinusoidal signal expression. Okay, generous sinusoidal signal expression. So we talk about sinusoidal means a sinusoid for sine. Okay, ST equals to A cos theta T. Okay, A cos theta T. So this is the angle. Okay, this is the angle. Therefore, we can change the amplitude and angle of the carrier signal in order to send the information signal. Okay, so here we can change the amplitude and angle of the carrier signal. If you change the amplitude, you're going to have amplitude modulation, right? Now you change the angle, so you will have an angle modulation or frequency modulation. Okay, or phase modulation. Frequency modulation, phase modulation, together they are actually angle modulation. Okay, so basic concept of angle modulations. Okay, so if you see so if you see cos, okay, if you see cos theta, okay, cos theta t is the one that you saw just now. Okay, let's say we go to the previous phase. You see here a cos omega, a cos theta t. Okay, so a cos theta t, I must write properly, so that it will be the same. So cos theta t, okay. This one is angle. Okay, angle. All of them is considered angle. Then we can further broken down. You will have omega ct plus phase. Okay, so this omega ct plus theta t is the angle here. Okay, so that's why you have this gradient for theta t equals to omega ct plus theta naught is an angle frequency omega c for sinusoidal signal. So if you see this graph, okay, you see this is the time as your horizontal axis. Then you have angle here. You have angle here as the y-axis. So you have this sinusoid signals. This one, these red lines, and then this one is you going to get the, if you want to measure the gradients. Okay, I think you learn this in your mathematics. I'm not sure additional maths or maths, but you learn, right? We can measure the gradient at each of these. Each of these points, we can measure the gradients. Okay, so taking this, for example, if you want the time sampling, you get, for example, this one, you can take this from T1 to T2, then you can measure the gradients. Okay, you can measure the gradients. So you see, if you take a straight line, straight lines, the blue one, then you measure the gradients, we take at 2 points. Okay, you know what is how to measure the gradients, right? Okay, difference in the y over the difference in the dt, okay, d theta over dt, you going to have to get the omega c. Okay, omega c is the omega c is what? If you radian over second. Okay, so this radian, so you have radian here, and this is second. Okay, then is omega c lah, radian over second. So here you can see, you can actually see is a relatable lah. Okay, so angle frequency, so it is an angle frequency. So omega is angle frequency, this one is f, but they are relatable lah. Omega is equals to 2 pi f. Okay, so gradient for theta t, omega ct plus theta naught is an angle frequency omega c for a sinusoidal signal. For a non-linear process, okay, for a non-linear process, theta t equals to theta xt, the gradient represent instantaneous angle omega I for sinusoidal signal. So this one, instantaneous means you're going to have different value of omega I at different time. Okay, that's why instantaneous. Okay, you cannot have the same omega I for across of the times. Okay, this can be seen at the time interval theta t. Okay, theta delta t, t1 and t2, both signals are the same. So you have a cos omega ct plus theta naught. Okay, this one. Equals to a cos theta xt. Okay, this is mathematics. Okay, therefore we calculate the instantaneous angular frequency omega I. Okay, is equals to d theta over dt. So this is valid for all but depends on which t that you are taking. So this one is instantaneous angular frequency. Then if you want to write in different form, you have this one. Okay, to show that it's an instantaneous angle frequency. The instantaneous angle value is given by the integration of from 0 to t omega it dt. Okay, if you see omega it is actually this one. Okay, integration of 0 t, and then this one you notice omega it dt is actually d theta over dt dt. So you can see, right, dt cancel out, we're going to have d theta. Okay, so that is an instantaneous. I don't know, I didn't put this. This one is from the slide. Okay, so therefore it is shown that information signal VMT can be transmitted with the amplitude of the carrier signal is held constant. Okay, in FM we don't disturb the amplitude, but in AM we change the amplitude, right? So that's why you need in the AM the amplitude is being changed, but the frequency is being constant. In FM, the amplitude is being constant, but the frequency is being varied. Okay, that's why frequency modulation, right? Okay, frequency, if you change the frequency, it will change the angle. Okay, the angle is the entire of this. That's why angle modulation. Okay. So therefore, it is shown that information signal VNT can be transmitted with the amplitude of the carrier signal is held constant and the angle, either the phase or the frequency. You can see. Okay, you can see either the phase or frequency of the carrier is varied linearly with the information signal VMT. So you can vary this one, or you can vary this one. You can vary the phase, or you can vary the frequency. This one is frequency, right? 2 pi f. Okay. And this one is phase, this one is frequency. Together they are angle modulation. Okay. And this one is phase. If you only change the phase, we can phase modulation. Okay. This one is frequency modulation. You change the frequency. Together angle modulation. Okay. But either one, okay, either the phase or frequency. Okay. And the instantaneous angle value, theta c equals to omega ct plus phi ct, which is this one. Okay. Therefore, the instantaneous angular frequency, which is omega, okay, and instantaneous angle value means value at that particular time. What is the angle value are given by? So this is instantaneous t. Instantaneous angular frequency at particular time is equals to d theta c over dt equals to omega c. Okay, omega c with a phase, instantaneous phase. Okay, instantaneous phase at that time. Then after that, omega ct here is actually the integration of omega I dt, omega ct plus phi ct. Okay, this is you can see is here. Okay, the phase, and also the frequency. This one is the angle, the entire of this. So this one is the illustration. If you have phi c, which is the phase, okay, the phase of the carrier, and this theta c is the angle of the carrier, the angle, the entire, okay, the entire angle. So for omega ct, you can see in the phasor form, okay, omega ct is the angle here, the angle that made by the first portion. Okay, this one. Okay, so this is this one. Okay, and next you have phase of the carrier. The phase of the carrier is this one. Okay? And together they form the angle. Okay, together they form the angle. Okay, and then this is omega it is the instantaneous, instantaneous angular frequency. Okay, so this one is actually straightforward. This one is straightforward. So this one is your amplitude carrier. Okay, carrier amplitude. So this one is phase modulation. So you know in the angle, inside the angle we have frequency component and we have phase component. So now we are discussing only in terms of phase modulations, means only this one. Okay, PM implies phase modulation implies that the phase deviations, okay, of the carrier, which is PC, is proportional to the modulating signal VMT. Means our phase deviation, our phi c will change according, will proportionally change with your modulating signal VMT. Okay, so we don't, means this one is fixed. We don't disturb this one, we don't disturb this one, but together, but because even though this is constant, changing of the phase will also changes the angle. Okay, because angle consists of frequency and the phase. So if you change the phase, even although the frequency is being fixed, in the end the angle will still change. Okay, then this phi c is relatable, okay, proportional to the modulating signal. So you have phi c proportional to your VM. Okay, VMT. I don't write T, but it's HET. And when it is proportional, we can. I found this on the web for OpenShift VM. Wait. My phone is full. Okay. So equals to a constant. Okay. A constant VMT. So this one is constant for phase modulation. That's why you put KP. Okay. Where KP is the phase deviation constant in radian per volts. Okay. So this one is logic because this one is angle, right? So it is in radian. Okay. This one is in volts. Okay. This one is in volt. If we have a constant, the constant times by the volt, the answer should be still in radian. So this one is a radian per volt. Huh? This one is logic, unless you don't get the logic, unless you don't understand the logic. Okay. So radian per volt. So you cancel out this, you still have radian, which is equivalent to this one. Okay. So Kp is the phase deviation constant in radians per volt. Okay. Therefore, VPMT phase modulation is EC cos. Okay. EC cos omega CT plus Kp VMT. Okay. Kp VMT, which is actually your phi C. Okay. Next, we go to the frequency modulation. Okay. Frequency modulation. FM implies the frequency deviation. Okay, just now is phase deviation, right? Now this is frequency deviation of the carrier. Okay, is proportional to the modulating signal VMT. Okay, so this one is your instantaneous, right? Instantaneous P. Okay, let's we see in the previous slide where the first is being introduced. You see here. This one is omega I, instantaneous angular frequency, is equal to this d theta c over dt, and you will have the carrier with the instantaneous angle value. Okay. It's proportional to the modulating signal VMT. So you have omega IT d theta c dt omega c plus instantaneous of angle value. So this one is equivalent to AF VMT. Same as well. Okay, proportional to this VMT. Okay, the frequency deviation. Okay, proportional to the modulating signal. Then, because it's proportional, as what you learn from mathematics, you can introduce a constant, similar like the phase modulation just now. Okay. So if this is radian per second, okay, radian per second, this one is measured in radian per second. Okay, this one is measured in volts. Okay, in volts. So what it should be, this one it should be radian per second per volt. Because if we cancel out this, you will end up still having radian per second, similar to the left side of the equation. So the K here is actually radian per second per volt. Okay. K. Okay. So if you see, this one is involved of the differentiation. Okay. So somehow it will we need to integrate. Okay, we need to integrate in order to later you will see the points of doing that. Okay, theta c is the angle. Okay, is the angle of the carrier. Okay, is the angle of the carrier equals to integration. Okay, integration from 0. You see the limit from 0 until t, and omega ct omega c plus kf vmt, which is this. Okay, we integrate it. Okay, means we integrate our omega I. Okay, we integrate our omega I here, pt. Then we will have omega ct okay, omega ct, then kf is a constant, we take it out, okay, and then integration of vmt dt, okay, then we will end up with vfmt, okay, vfmt, frequency modulated signal, not modulating, frequency modulated signal is equal to ec cos omega ct plus kf, our frequency deviation constant, integrated of your vmt dt, okay. Okay, now we're going to see the relationship between frequency modulation and phase modulation, okay, because they, all of them are a part of angle modulation, So first, we're going to see the generation of our FM, of our frequency modulation signals. Okay, means we changing in terms of this omega. This phase modulation, we change in terms of our phase. Okay, so VMT, the signal we integrate. Okay, we integrate the signals. Okay, V means VMT means integration of VMT dt. Okay, so we're going to integrate them. VMT, VMT dt, VDT, okay, VMT dt, and then we go through a PM modulator, okay, phase modulator. Then we have a frequency modulated signal, which is VFM EC cos omega ct KF VMT. This is the one in the previous slide just now, the recent slide before this one. Okay, in generating PM phase modulation, instead of integrating as in the frequency modulation, we differentiating it. Okay, and after we differentiating it, we go to the FM modulator. Then you will have PM, phase modulated signal. Okay, phase modulated signal. So VPM equals to EC cos omega ct plus Kp, phase deviation constant, VMT. Okay, we can generate FM signal by using PM modulator and vice versa. You can see, right, there is an interrelation. If you want to generate PM signal, you're going to need FM modulator. If you're going to generate FM signal, you're going to need PM modulator. Okay. If you want to generate FM modulator, you need to have PM modulator. If you want to generate phase modulated signal, you need FM modulator. Okay. For the above block, it can be shown that the generation of AM and PM are mutually related. Yes. Even later on in the receiving part, also almost similar related. Okay, so this is the demodulation part at the receiver part. So if you see VFMT, frequency modulated signal, we have the integration part, right? When we have integration parts, means we're going to have a differentiator. Okay, the opposite of it. That's why you have differentiator here. And this one is the differentiator, right? Differentiated signal. Involved differentiator in the previous slide. That's why we're going to integrate them. Okay, it's the opposite. Opposite. So VFM signals, if we go to the PM demodulator, okay, we can see here at the generator part for the FM, we have PM modulator at the generator. Then at demodulator, we're going to have the same PM but PM demodulator. Okay, so it should be that in FM signal we have PM modulator at the generator part. At the demodulator, we're going to have PM demodulator. Okay, similarly for the PM modulated signal, for phase modulated signal, if you have FM modulator at the generator, you're going to have FM demodulator at the receiver side. Okay, then you're going to have integrator. So then in the end, you're going to have the same message signal or modulating signal, okay, or information signal, the one that you information that you want to transmit and receive. Okay. So demodulation is used to get the back the information signal. Yes, information signal, modulating signal, message signal, many names. For FM demodulator, in order to get back information signal from FM, PM demodulator is used. So this is what basically what I told you just now lah. Okay. In contrast for PM is the same. In contrast. This shows that the close relationship between FM and PM. Okay. Hence, we can discuss only either one technique in angle modulation because they are relatable to one another. Okay. So we will discuss either one of the technique in the angle modulation. Okay. Because angle modulation involves this FM or PM. Okay. In angle modulation, you can have frequency modulated signal or you can have phase modulated signal, and by seeing the generation and generation and demodulation signal, you see that they are relatable. So that's why we only discuss only either one of the techniques. Okay, they are similar. Okay. Next is the analysis of this FM signal. Analysis of the FM signal. I thought I'm going to. Okay. So analysis of this FM signal. So assuming that the modulating signal VMT, this one is you already familiarized, right? Okay. So with this kind of writing, okay. Assuming that the modulating signal VMT, your information signal, your message signal. So EM cos omega MT, substitute in the equation of the FM. Okay, now we only discuss on FM. We not discuss on phase modulated signal, but they are relatable to one another. That's why we discuss one of them. Okay, so this one is FM. FM. So we substitute this EM cos omega MT inside this. Okay, inside this VMT integrated. Then you will have VFMT EC cos omega CT plus KF. Then integration of EM cos omega MT dt. Then you have EC cos omega CT plus KF over omega M EM sin omega MT. So you see this cos omega M, when we integrate cos, we will have sine, right? When we integrate cos, we're going to have sine. This one I cannot help you. This one is mathematics, okay? Actually, before coming to this course, you should have a strong mathematics skill, including trigonometry. Okay. If you're lucky, this trigonometry is in the appendix that maybe you need to use, or if not, you need to able to use your own trigonometric skill. Okay. But it's in the appendix. But I'm not sure if the appendix provide all. Okay. But actually, you don't. Actually, you should have some trigonometric skill. Okay. Because it's engineering, we are engineering student. I also a student. We need to have strong mathematics. We cannot put all everything of the simple formula inside. You need to be able to have strong mathematics skill. Okay. So here, when we integrate cos, we get the sine. Okay. And then it's not finished there. Then the omega m should be put outside. Okay. So for the integration, cos will become sine, or sine, when you integrate, you will get cos. Okay. But whether it is minus cos or plus cos, this you need to figure out yourself. Okay. But it's easy. Actually, you can Google, or actually you try to memorize. Okay. This is you learn this trigonometry since secondary school. Okay. So we have cos, you integrate, you get sine, and then omega mt, you differentiate, then you get this omega m. Okay, you get omega m here lah. Okay, and then kf is a constant, that's why it's out. You just put it out, so it's not going to be integrated. It's just a number. Okay, kf em is also a number, so we just actually integrate this one. We just integrate this one. Okay, then identity that being used here, cos ax dx equals to 1 over a sin ax. Okay. This one, of course, in the slide we give, but in the exam, not necessarily you have this, but so that's why hopefully you have a good skill in trigonometry. So VFT equals to EC cos omega CT, and then you have this group. Okay, this one can be simplified, okay, with KFEM. KFEM is equals to delta W, okay, which is the maximum frequency deviation, not frequency deviation, but the maximum frequency deviation. Okay, maximum frequency deviation. So delta omega over omega m. Delta omega over omega m. Okay? So this one is actually equivalent to your delta omega, which is frequency maximum frequency deviation. Then you see, then you have this as delta omega. Then you have omega m, which is your the angular frequency of your modulating signal or message signal. Then they are actually beta, which is the modulation index. Okay, modulation index in frequency modulation is using this symbol omega beta, but in AM modulation we are using M as a modulation index. Okay, so define the modulation index as a ratio of maximum frequency deviation, correct, because this one, over modulating signal frequency, which is your omega m. Okay, so if we want to simplify further, we remove the 2 pi 2 pi, so you're going to have in terms of frequency. If in terms of angular frequency, it is like this. Okay, hence equation Fm will be yield, or you can simplify further to have this in terms of beta. Okay, so as you know, beta is actually just like this. Okay, and then this is what? This one is KF EM. I'm not sure if in the appendix is they give you or not in the appendix. Yes, in the appendix they give it to you. Okay, they give it to you in the appendix. Okay, what is beta for the FM? Okay, but you need to know where to put it. Right? If you don't know, given the appendix, also maybe if you find it's hard to relate. Okay, but you should know where is this beta is being placed. In the FM, in the FM, in the FM, it is here. Okay, so you have VFMT equals to EC cos omega CT plus beta sine omega M. You see, this one is omega M, this one is omega C. So using this trigonometric identity, cos A plus B, okay, this one is inside, given inside your appendix. Cos A plus B equals to cos A cos B minus sine A sine B. Okay, so hence, if you expand further, okay, you see here, this cos, this one is taking as A, this one is taking as B. Okay, so cos A cos B is equals cos A cos B means cos omega CT, which is A, plus cos B, which is beta sine omega MT. Then you have minus, okay, and E sine A omega CT and sine beta sine omega MT. So where cos beta sine omega MT, okay, which is this one, okay, sine omega C omega T is a trigonometric series called as a Bessel function. Okay, so if you look into the appendix, okay, if you go to your appendix, okay, you can go to your appendix. You start to have the wording as a Bessel, Bessel. So appendix page 3, you have Bessel table, then you have area function table. You can see the Bessel table there. Okay, modulation index, beta, alias, MF. Okay, so if you have beta, is 0.25, we're going to have coefficient J naught equals to 0.98. With sideband, you only have first sideband. You only have one sideband. Okay, don't worry, we'll go through this later on. This Bessel function or whatever later on. Okay. So expand using Fourier series yields. So this one you learn in your signal and system subject. Okay, expand using Fourier series, you will use cos beta sine omega mt is equal to j naught beta. So because this is even, right? Okay, this is even. You learn in your signal and system. Cos is an even signal because they are similar in terms of if we place a mirror here, it looks similar. It's even. So that's why it's even. So that's why you have even here. Okay. And sine is actually odd signal. I think you know as well. It's because it's like this. Okay, it's like anti-symmetric. Okay, it's odd, odd signal. Okay, you learn this also in signal and system. So sine beta sin omega mt is equals to 2jn beta sine n omega mt. This is an odd signal. So I'm not sure if this is okay. This one is also in appendix. So like you, this one is also in appendix. Okay, appendix page 2. You can see they put the cos beta sin omega t equals to blah 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 and so on. But in the you must be careful in the appendix. They didn't mention even or odd. They just mention for example cos beta sin omega mt is equals to j naught beta plus 2 sigma n equals to 1 until infinity and j2 beta cos 2 n omega, and the sign they put as 2 n equals to 1 infinity blah blah blah. Okay, so this one is not yet later we'll go through this later. Okay, more on this. So if we substitute into our VFM, okay, if we substitute the this one, this angle that we obtain here in terms of this Fourier series, okay, we put inside here, okay, inside this equation, which is earlier we have EC cos omega ct and EC sin omega ct, right? So this one will be cos will be yeah. This one will be inserted to here, okay, and this one will be inserted to here, okay. Mean substitute, okay, we substitute. So substitute you will have an even longer, but don't worry, this is just logic and straightforward, and this one is as well accordingly, okay. Then you're going to have the Fourier series of this frequency modulated signal, okay. Okay, so here is you expand them, EC cos j naught beta. So you expand this. And then the next is 2jn beta cos n omega t times with this cos omega ct. Okay, so that's why you have this here. Okay, and even and 2 omega 2 EC. Okay, and the similar is here. Okay, and this is just expansion. Just expand it. Okay, try this one by one at your free time. Okay, so that you understand. Don't just take this edit list. Okay, then using Bessel identity. Okay, Bessel identities. I'm not sure Bessel identities is it being put in your appendix? No. Okay, this one is not in your appendix. Okay, this one is not in your appendix. So either you need to memorize it or not, I'm not sure. But if you need to memorize, not so much, because yes, this is not so much complicated compared to the other equations. So j negative n beta, okay, j negative n beta is equals to negative 1 n, j n beta. So for example, if you have j equals to negative 2 beta, okay, so you're going to have negative 1 J2 beta. Okay, then it will be 1 1 J2 beta. Okay, J negative 2. So what if you have J negative 3, but you have J negative 4? Okay, you can try this at home. Okay, so hence FM equation also known as wideband. Okay, this is wideband FM. Okay, FM equation also known as wideband. We will going to have more and more sidebands. Okay, so you learn in signal and system, right? Signal system, you can have a lot of this is will contribute to more sidebands. Okay, means here you're going to have sidebands. Okay, so expand the equation will yield endless like this. Okay, because you can see it's negative infinity, anti-infinity, but we can define, for example, negative 5 to 5, negative 6 to 6, and so on. Okay, so this the fundamental. Then you're going to have, for example, this is the first one, sideband one. This one is the carrier band. This one is the carrier band. This one is the sideband one, J1. And this is the sideband 2. Okay, this is the sideband 3. And this is sideband 4, and so on. That's why you have N here. Then you're going to have N here. Okay, so this one is up until sideband 4, and sideband N is you can increase further. So that's why it's wideband FM. So this is okay. Frequency spectrum of FM signal, okay, is the number of sideband depends on the beta value. Okay, depends on the beta value. If you look into your Bessel table, appendix Bessel table, if you have beta 0.25, okay, if you look into your Bessel table, so beta is 0.25, you're going to have the first coefficient J naught equals to 0.98, and then the first band is 0.12. So this one is J naught times EC, means J naught is 0.98, J naught 0.98 times with your EC value. EC didn't give, right? We didn't have EC yet. Okay, so if EC is 1, for example, then the amplitude here will be 0.98. If EC is 2, is 2 times 0.98, and so on. And similarly with this one, J1 is 0.12. Okay, if you look into the Bessel table, 0.12, and let's say if your EC is 1, so you will have 0.12. If you have beta equals to 2, if you look into the appendix page 3, if your beta is equals to 2, means you're going to have until 4 sideband. That's why you have 1, 2, 3, 4. And then 1, 2, 3, 4 sideband. And accordingly, you see J4, for example, is 0.03. So 0.03 times 1, let's say is 1. Let's say we take EC equals to 1. Let's say we take EC equals to 1. So you can see the value will be like going down, smaller, but you can see the value there. And then your EC, then your this first will be 0.22, 0.22, okay, and so on. And then the bandwidth calculation is for the beta, for the bandwidth is 2NFM, 2NFM. So because your N is 4 in this case, 4 sideband, so 2 times 4 times FM, so you're going to have 8 FM. Okay, this one is because for beta 5, you're going to have until 8 sideband. So that's why 2 times 8, 16 FM. Okay, 16 sideband. So this is the phasor function. We already discussed, so no need I discuss further. Okay. This one is Bessel function plots. This one, this one is Bessel function table. If your J This one is actually almost similar. Okay, for example, if you have beta, okay, this is your first sideband. This is your second sideband, and so on. So first sideband means FC plus FM. Second sideband FC plus 2FM, FC minus 2FM. Okay, for a low modulation index, the amplitude of the higher sideband fall off rapidly. You can see actually, right, the amplitude is going to fall off. So if you have low modulation index, okay, if you have beta, which is small, okay, you can see the amplitude of the higher sideband fall off rapidly. Okay, so if you have big beta, it's different. Okay, you see from the previous this one. Okay, if you have beta is small, you can see it is fall off rapidly lah. But if you see if the beta is higher, it's slowly, okay, slowly fall off. So you can look this one Bessel function for n0 to n4 sideband lah. Depend for the number of sideband from n0 until n4. Okay. Maybe we will look into this in the later class. I'm not sure. Later I will look into the module. Hopefully module have exercise. Because if we go straight to the test, maybe you will find it you need to learn simple things first, then you learn a bit more challenging, something like that lah. I will look at the module. Okay, and you can read the module as well lah. Okay. So the summary of a FM spectrum, frequency spectrum consists of carrier component at FC and also sideband at FC plus NF and FM. So depending how many sideband you're going to have. If we have two FM, where n is an integer with n 1, 2, 3. Okay. The number of sideband depends on index modulation beta. Okay. If you have more higher number of beta, you're going to have more sidebands. Okay. If you have higher number of beta, you're going to have more sideband number. And if you have if you have bigger number of beta, the fall off is more smooth. Okay, I mean it's not rapidly. But if you have small value of beta, so it will be very fall off rapidly. Okay. Magnitude of carrier signal decreases as beta increases. Okay, as beta is increased, the magnitude of the carrier signal decreases. Magnitude of the carrier signal EC decreases as your beta is increases. Okay, inverse. Okay, amplitude of the frequency spectrum depends on value of Jn beta. This one is correct if you refer to the Bessel table and if you refer to the Bessel graph just now. Okay, the bandwidth of modulation signal increases when index modulation beta is increases. Okay, bandwidth equals to 2 delta FM is expected. Okay, if you have you can see the bandwidth is increased, right, when the beta is increased, because beta, when you increase the beta, the number of sideband is increased, so that's why your bandwidth will be increasing accordingly. Okay, this is very relatable. Okay, so we will touch on the Carson rules in the next class. Okay, so thank you for listening. Only 4 students, but it's okay. Class will move on. Okay, thank you. Assalamualaikum. See you in the next class.